Hello. So, today we will start our next and last module, that is module 4 on case studies. Now, here we will actually discuss on one or two particular sensor of MEMS field, okay. But before going to that, let us revisit once that what are the different things we learnt. In the first module we learnt about in general what is a MEMS sensor, how does it work, and then why we need to go down to like micro or nano scale, and what does it change actually in that once we are going from macro to micro or nano scale. And then we studied different mechanical structures and how what is the relation between the force and deflection. If we apply some force, then how the deflection will be, or how the deflection will be related to the force. And then also we learned that how, in the second module we learned that how we can actually measure that deflection using capacitive method or electrostatic technique. And then in the third module we discussed about different sensors fabrication, like what are the different fabrication technique, how we remove a material like etching, how we deposit a material like evaporation, and different kind of coating techniques. And now we are going to discuss on a particular sensor, and first our first case study will be on pressure sensor. So let us discuss about pressure sensor. So what are different types of pressure sensors? For pressure sensors, we know that what it does, it actually measures the pressure of the gas or pressure of the liquid in a chamber, which whatever is our requirement. Now what are different kinds of pressure sensors? The first type is absolute pressure sensor. And in that we measure pressure relative to vacuum. So in case of absolute pressure sensor, we measure the pressure relative to the vacuum. If we consider vacuum to be zero pressure, then whatever pressure we measure with respect to zero, then that is our absolute pressure sensor. Like atmospheric pressure measurement is example of absolute pressure sensor. Next is gauge pressure sensor. Here we measure pressure relative to the atmosphere. Atmospheric pressure. Then we have like differential pressure sensor. Okay, before we go to differential pressure sensor, what is the application of this pressure? Like blood pressure, right? So blood pressure, while we measure a patient's blood pressure, that is relative to the ambient or the atmosphere, right? So that is an example of gauge pressure sensor. On differential pressure sensor. here what we do, we actually measure pressure or measure actually difference of pressure between two different pressure measurements. So, let us say you have an application such that you have two chambers and you have to measure the pressure difference between them. So, in that case we can use this kind of differential pressure sensor, and example is like high pressure oxidation chambers or things like that. Now, pressure sensor working principle. So, this is the general diagram of a pressure sensor, where we have a membrane like this, as you can see here we have a membrane, and then here is the pressure port, right, and the top side is can be vacuum or can be atmosphere at like atmospheric pressure or some other gas pressure also, depending on what kind of pressure gauge it is, like whether it is absolute pressure sensor or differential pressure sensor or gauge pressure sensor. Accordingly this top side will be decided. So, let us assume this is packaged under vacuum and this side, the top side, is vacuum. Okay. Now, this is the pressure port of which actually we are measuring the pressure. So, this is connected to some chamber, this is connected to some chamber of which pressure we are measuring. Now, as the pressure or the gas pressure comes, then what it will happen, it will have like ballooning effect, and this membrane will be deflected, this membrane will deflect like that little bit. Okay, and we will measure this deflection of the membrane by some technique and can calculate the pressure. Now, like for this case, if we have the membrane of size 2A and let us say the thickness of the membrane is H, then from the theory of plates we can write that P equal to E into H to the power 4 by A to the power 4 into 4.54 W0 by H, where W0 is the deflection of the membrane, plus 2.33 into W0 by H whole cube. So, here this is the expression and this comes from theory of plates. Which is not part of this course, and this is the basics mechanical course actually. From that we can derive this expression. Now, what is this E? This E is Young's modulus. H is the thickness of the membrane, A is the like 2A is the total length of the membrane, right, and so A is the center, like distance from the center, like from the center to the periphery, it is A. W0 is the deflection of the membrane, right. So, W0 is deflection. And so, all of these terms like H is a geometry property, right. Whatever dimension we make the membrane, accordingly we know H, we know A, and we know E, this is material property, and if we can measure W0, then we can get P very easily, like what is the using this expression we can calculate the pressure. Now one thing we need to understand is this P is the difference between the top side and the bottom side, and as the pressure changes, accordingly we will have the deflection. Now deflection, this deflection pressure is the nonlinear function of deflection for any general deflection, right. But if the W0 is pretty small, if W0 by H very small than 1, then what we can write is pressure changes linearly with deflection, because we can then neglect this W0 by H whole cube term, and accordingly we can just get P varies with W0, or this is linear. And most of the sensors while we apply for real application, we actually need this kind of linear relation, because it makes our analysis and use easier. Now what is the basic concept of this pressure sensor? As we have shown that there is a pressure port through which the which is connected to the membrane, and as we apply some pressure, the membrane deflects, right, because it has in this region the pressure is different from compared to this region, so the membrane will deflect. Now we can put some sensing element on top or some sensing technique to measure this deflection, right, and accordingly we can measure the pressure. Now what are what can be chosen as membrane? First is our first option, or the most popular option, is single crystal silicon membrane, because the creep, fatigue or hysteresis effect are virtually absent in that case. So whatever let us say we apply some pressure, and after we release that, if we remove that pressure, then the membrane comes back to its original position, okay, without any creep or fatigue. And for silicon, actually the Young's modulus and its deflection properties are very well known and standard. So it is usually silicon or SiO2 membranes are used for this kind of pressure sensors. Now for sensing element also we have different options. One option is piezoelectric sensors. So piezoelectric sensors means that while we are putting this sensor, this will be a piezoelectric material. Now what is the property of piezoelectric material? It is, if we apply some kind of stress or strain on the piezoelectric material, then it generates some voltage, okay. So let's say this is a cantilever or membrane, and on top of that we have some piezoelectric material. Then as we deflect or apply some stress, then this piezoelectric material is also under that stress, and this will generate an electric voltage at that element. So if we can measure that electric voltage, and then accordingly we can measure how much is the deflection and how much is the pressure. So this is one case. Another case is capacitive. Like as you can see that in the like one of the previous module, you have seen that capacitive, how does capacitive measurement work for electrostatic case, right. So as the membrane deflects, the distance between the top plate and the bottom is different, right, because it has now become like a bulge, and this minute change in the deflection can be captured by its capacitance, but because capacitance for parallel plate arrangement is C equal to epsilon A by D, where D is the distance between the two plates, and so we can measure the distance between two plates by measuring their capacitance also. Another is piezoresistive. So in this case what we do, the material we put has a piezoresistive material, right. So piezoresistive material, what happens is, as we apply the force, then in the piezoresistive material the resistance of the material actually changes, and because of that, if we can measure the resistance, then we can measure that how much is the deflection and how much is the pressure generated. So let us move to the first case, that is piezoelectric sensing. So, as I was saying that there will be a sensing element which is piezoelectric, and piezoelectric element, one of the very popular example is PZT or lead zirconium titanate. So, this material has such property that if it is if some stress is applied on that material, then some potential will be generated, and that potential we can measure to measure the applied stress or the to measure the pressure. So, the first point in this regard is piezoelectric crystals like quartz, let us say PZT, gives electrical output under an applied stress. And why this stress is coming? Because the pressure is making the membrane to deflect or bend, and because of that piezoelectric element, this stress will be applied. So, this is one point. Now, another is this does not need any external power. So, as the voltage is itself generated inside the material, we does not need to apply some voltage in this case. So, that is one of the advantage, but the limitation with this technique is silicon is not a piezoelectric material. So, what happens is we need to actually externally glue or do something or deposit some PZT material on top of that, which is not very convenient all the time with microfabrication technique. So, this is one of the disadvantage of this technique. Another is that static pressure measurement is difficult. What does it mean? Means that let us say we have some we are applying some pressure, then this piezoelectric material will be under stress, so it will generate some voltage. Actually what happens that it actually have some charge separation, and that charge separation will give us the voltage. Now if this pressure is constant at that point, then the charge also need to be static at that at the two different plates or two different electrodes, but it always does not happen, because there is always some kind of leakage happening in between the two plates, because this material is not a perfect insulator. So the charge will leak, and with time we will see the voltage again comes like voltage decreasing, the generated voltage decreasing, whereas the pressure is same, right. So in that case it is actually little bit difficult to measure static pressure. It does not because of the charge leakage, it does not keep same output voltage. But if the let us say the membrane is vibrating, so in that case what is happening is that the charge generation is changing with time and with a high frequency. So if it is changing with a high frequency, then in that small time period it does not have time to leak through the insulating material or to the PZT material. So in that case we can measure the charge oscillation and can measure the how much frequency or amplitude is the membrane having. So, in those dynamic cases we can use this kind of piezoelectric sensing. Next is capacitive pressure sensor. So, in capacitive pressure sensor we have the same kind of arrangement. So, we have a diaphragm like this, and on the top side also we have a plate. Now, as let us say this is actually connected to the bottom side is connected to the pressure port. So, as the material, as the gas applies some pressure, this membrane or diaphragm actually deflects, and accordingly the distance between this, like the top plate and bottom plate, this distance changes, and that actually, as we have discussed in module 2, that changes the capacitance or the capacitor of these two parallel plates, right. And so, the first point is that detects the deflection as a variation of capacitance between the two plates. The important advantage of this is high sensitivity, very high sensitivity. Why this is high sensitivity? Because you see C varies with 1 by D, right, and little bit of change in D will change the C by a significant amount, and this D will change because of the applied pressure. So, we can measure the change in D using capacitance, and from that we can measure the pressure. Another advantage or merit of this technique is absence of temperature sensitivity. If we assume that there is no effect of temperature on the deflection, like or whatever be the pressure, if we change the temperature also there will be no change in the deflection, then like pressure to deflection is not dependent on the temperature, and then according to our parallel plate capacitor formula, already we know that that is also not dependent on temperature. C equal to epsilon A by D, which is not dependent on any of the temperature term. So, we can consider this is temperature insensitive. So, at different temperatures actually we can use this technique, which is theoretically, but because in practical cases sometimes this epsilon value also changes with temperature. If the temperature changes by huge amount, then the epsilon can change, and so that time temperature sensitivity may come. But if we consider the other cases like the piezoelectric or piezoresistive cases, then it has a temperature sensitivity, because with temperature the piezoelectric coefficient also can change, and also the piezoresistive coefficient also can change. So, this has a higher temperature sensitivity compared to the capacitive pressure sensors. But one of the we can consider it demerit if we see the in case of piezoelectric sensor we already getting a voltage output. So, we do not need a real conversion from one kind of parameter to another, but here we need electronics circuit for C to V0, let us say the output V0 conversion. So, we need to connect some kind of electronic circuit which will convert the capacitance to output voltage. And another thing is that this C to V is not linear. It is not easy to make a conversion circuit which will where the applied voltage. So, ultimately whatever voltage output we will get, that voltage output may not be linear with the capacitance. So, that adds one more complexity in the sensor. So, we will start with the piezoresistive sensor in the next class. Thank you.